I am Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics at Arizona State University, and I'm here to do a general introduction of nuclear magnetic resonance, specifically associated with the Magnetic Resonance Research Center at Arizona State University. And so, what can the Magnetic Resonance Research Center do at ASU? Well, it's primarily used for NMR to do structural elucidation or structural characterization of molecules, of typically organic molecules, organometallics, inorganic systems doing solids, etc., where we can look at anything from small organic synthesis, inorganic synthesis, to large biomolecules, proteins, nucleic acids, etc. But besides that, you can also do things like looking at diffusion. You can do some micro MRI of small samples, look at reaction dynamics in systems, kinetics and equilibrium. So this is really one of the seminal techniques in the molecular sciences to be able to look at the molecules both structurally and dynamically of a system. And so the hardware we have available in the Magnetic Resonance Research Center ranges from high field NMR systems, which are most typically used for elucidating biomolecular systems, proteins, nucleic acids, etc. Solids NMRs, where we often run this, where we need to spin the sample to do averaging to get high resolution solids NMR for oftentimes materials, material compounds, etc. We have fully automated systems, so people in the middle of reactions that want to check things can come and quickly get automated, and also remote people and online students can send samples where they're automatically run and the data is made available on the cloud for students to be able to access, etc. So we provide examples of hardware in the facility to show what some of the internal hardware and instrumentation looks like. And this over here kind of shows what your most common sample looks like, which is just a 5 millimeter 5 millimeter NMR tube where you have a solvent in there, which is deuterated. You put your compound of interest to do liquid state NMR to look at molecular level structure and dynamics associated with a molecule of interest. And this is me putting it into one of our Bruker 400 megahertz automated NMR systems. And this is one of the most common ways that students and researchers interact with an NMR nowadays is that we put it directly into an auto sampler, Sample Express, and just get our data online for the system. Now, the fundamentals of NMR, which we'll cover in classes at ASU, from looking at both modern magnetic resonance class, which I teach, and we have several other faculty at ASU whose focus is magnetic resonance, that teach everything from the fundamentals to the practical of doing protein and biomolecular type NMR to practical small molecule structure elucidation, etc. And at the heart of this, we're looking at the fact that we have the fundamental particles that make up atoms, electrons, neutrons, and protons, all have a spin or an intrinsic angular momentum associated with it. And this causes the nucleus of many of the elements or atoms that we deal with to have an intrinsic angular momentum associated with the nucleus of an atom. And so it's not every isotope, but we show a periodic table here of ones that have an overall nuclear spin of 1/2, like proton, like carbon-13. It's a specific isotope. Like fluorine-19, even some of these that are quadrupole, N14 is a quadrupole, but N15 is a spin 1/2. system. And so we can look at these systems by putting them in a large magnetic field and be able to look at their nuclear magnetic resonance. So the nuclei of interest that has a non-zero spin, we're able to look at its magnetic resonance properties. And this can tell us a lot about the structure or the molecular configuration and dynamics of a molecule. And so, so specifically when we put it into magnetic fields, instead of having random spin orientations, we get alignment with the field, and we get a net overall alignment with the field depending on how high of a field you go to and what temperature you're associated with. And one of the things that makes NMR so useful from looking at molecular level details is the idea that the electrons that surround the nucleus, they can add a shielding property because it's a charge moving around. It creates a magnetic field itself that can shield the primary field that we're associated with, the magnetic field that we put our sample into. It can shield it from that by small amounts. And therefore, we can get this chemical shielding because it's the chemistry of how the electrons are bonded to, are being shared across different nuclei in a molecule. And it gives us different chemical environments, for the different nuclei that make up a molecule of interest. And so from this, we can get a very good sense for the different electronic environment of each nuclei in a molecule of interest. Now, it's very important that we have the main field that we apply to be as homogeneous as possible, meaning the magnetic field is the same throughout the entire sample. And like I said, the most common sample is just a 5 millimeter NMR tube. So a 5 millimeter diameter and more or less very long in this direction. But typically a typical volume is about 0.5 to 1 milliliter of total liquid here. And the volume that's being looked at is roughly in this area right here is usually a little less than half a milliliter of total sample volume. And you want the magnetic field throughout the entire sample that's being interrogated here to be the same throughout, so that really there's no difference in field that would cause it to have different precessional frequencies just by the fact that different parts of the sample are in slightly different magnetic field. And this just shows you. Now, that magnetic field gradient is used to spatially encode in MRI. But in nuclear magnetic resonance, where we want to look at the chemical differences, we want the field to be as homogeneous as possible. And this is typically achieved by what is called shimming the magnet. So using just slight field variations where we put current through coils to basically move the main magnetic field so that when you put the sample in there, it is as homogeneous as possible. And nowadays, this is done in a fairly automated way. And so if we have our sample where it's locked to a deuterium signal and then shimmed, which is now done usually very in an automated sense, the most common experiment is just a single pulse where we use another magnetic field that we typically call B1 to rotate the spins, and then we watch them come back to equilibrium. And so we usually say we put our sample in there, we have an excess of a magnetic moment in one direction aligned with the main static magnetic field. We usually do that in the Z direction, and we usually call the main static field B0. We do an excitation, and we usually call that B1, and that's an oscillatory magnetic field, so that it causes the overall magnetic moments the bulk to rotate. So we rotate them away from equilibrium, and then we watch them return. And they return with different, so there's a dephasing in the transverse plane, and then also a return to equilibrium in the longitudinal plane, or the plane of the static field. So, and then oftentimes this is, in a sense, repeated. And it's repeated by the number of scans. And that's typically, oftentimes a binary. So like something at 8, 16, 32, etc. Just as many scans as you need. And there's several parameters that really go into looking at this. How long you wait before you do this, how much data you collect, that you collect the entire free induction decay. So this is a function of time, and then we'll Fourier transform this to get it into frequency space. And so this is showing that you can vary the length of the pulse to rotate it, say 90 degrees or down to 180 degrees or even further. And so if you do this systematically, this is typically called nutating your spins to find out what, for example, the ideal 90 degree pulse is, that we'd write that way, or 90 degree as a pi over 2, etc. Well, this would be a pi pulse. And we're almost always referring to this as that the static field that we put it in the z direction, and then we're usually using a oscillatory second field for excitation that is typically transverse to that. And this just shows a common thing to worry about, which is if you don't, for example, make the recycle delay long enough, even if these started off where you would expect it to be quantitative, where these should be at a 1-to-1-to-1 ratio, if you don't wait long enough and it doesn't fully relax, so for example, this B spin is not fully relaxed before you collect the next scan, etc., you can end up after a certain number of scans looking at things where it doesn't seem to have the right ratio, and that has to do with that you didn't wait enough of a recycle delay. And this is just one example of the parameters in NMR that typically need to be looked at, and you need to have some familiarity with to be able to set up NMR experiments correctly, so that you're collecting things in a quantitative way. You have a homogeneous field so that you're able to collect them with as much resolution and sensitivity as possible. And one of the common things that we do first is run, some simple molecules so that you're able to look at some of the basics of this. And so ethyl crotonate, shown here, is a very common sample to start with, because it has several common groups, whether it's carbon double bonds, this basically acid group here in the middle, where you have a bunch of different chemical environments, and it really will help illustrate what we look at as the J coupling between these, or in other words, the indirect spin coupling through the electrons, it's specifically through bonded electrons or shared electrons between two different nuclei. And this is very useful to be able to give molecular level details. So besides just the chemical shift itself, giving some indications of what the electronic environment is, the J coupling is probably, also one of the most important things to chemists to really resolve molecular level details of the bonding of a molecule. And this one's very commonly used to kind of set things up. And in fact, it's used a lot in a book like this 200 and more NMR experiments. Sample prep, that you are able to get good NMR tubes, which often means they're extremely thin glass walled and very, they look like an infinite cylinder, so they have very tight tolerances. You need to be careful with that because they are very thin walled, they're easy to break, etc. But this allows you to get as homogeneous of a field as possible. And then it's often very critical that you get the right levels in here, the right amount of materials, so that you really can shim your sample as good as possible. And when you're running carbon-13 is specifically, it's critical because of the insensitivity of carbon-13, that it's typically only 1%, and its gyromagnetic ratio is significantly lower than proton, that you need, enough sample to be able to look at it properly. And then, the solvent that we put the molecules that we want to look at in need to be deuterated. And these are deuterated, one, so that they don't contain protons that basically swamp out, that have such a higher concentration that the molecule that's dissolved in it, the solute that we want to look at. But also we use that to field lock so that we can stay as homogeneous as possible. So it's locked to a deuterium signal that relaxes quickly, and we use that to both shim and lock the sample so that during the course of the experiment, the field is, the B0 field, the main static field, is as homogeneous as possible. So, and, as we've seen before, the most common thing to do is to do a single pulse proton type experiment. The data that you collect is called a FID, a free induction decay. But oftentimes what we do is immediately go from kind of a time domain to the frequency domain. So we do a Fourier transform to get that to the frequency domain to show the spectra. In fact, most modern spectrometers don't show the raw data, which is the free induction decay. They show the resulting spectra that comes off of it in frequency. And the most common is to show it in parts per million of the field, so that it doesn't matter what strength of magnetic field you're looking at. And so what we say here is that we use an RF pulse to flip our spins. Then we record the free induction decay as they return to equilibrium. And then we Fourier transform to look at all the different frequencies. And if we've done this such that we wait full relaxation times, then it should also in proton be quantitative, or that the integral of the area under the curve is quantitative to the number of protons associated with that. Now, it's also showing here that the pulse we use, excites a certain frequency domain. And this comes again because of the Fourier transform, that the shorter in time, the more in frequency space. And so we usually use these pulses such that they excite the entire frequency range of all the nuclei that we're interested in. So that it basically excites the entire proton chemical shift frequency range. So for more information, this is meant to be just a general introduction. I'll provide at my website, biopchem.education, some links as we start going through different courses at ASU on practical NMR and modern magnetic resonance, etc. All of the general information will be on this website. Also, there's a lot of resources available, from online kind of textbooks that I give here, the basics of NMR, to one, like I said, I showed you earlier, where oftentimes when you're sitting in front of a spectrometer, this is a really great book to go through the different types of NMR experiments: proton, carbon, heteronuclear experiments, homonuclear 2D experiments, relaxation experiments, diffusion experiments, etc. There's a whole range of different types of spin interactions you can look at in different experiments that need to be done to resolve different types of molecular interactions. And this is a good book to kind of go through some of that. Also, as far as some of the basics, the fundamental concepts, so that you better understand not only how to analyze NMR, but just from a fundamentals perspective, what nuclear magnetic resonance is, its fundamentals, which help in how to set up things properly and analyze data, from things very specific like this book on protein NMR, where it goes through both the principle and practice of and interpretation, etc., to understanding NMR spectroscopy, where it goes